Hey guys, forgive me on the lateness on this one. It's taken, let's say, 2 hours to type up. For the record, the casserole was all right. I might have overcooked it. All right, so today we're going to do a warm-up problem. I figured, it's the weekend and it's good that we do a little bit of exercise. And then there's an extension to that problem, which is definitely worth the watch. It's some incredible mathematics, hence why it took so long to put together. Alrighty, so problem 9a. Prove that. Alrighty, solution time. It's not a difficult one. We just get things up, similar to the previous problem from yesterday. We take those cosine A and cosine 5a terms, put them together using the sum to product formula. Same thing for the blue terms. Factor out a common factor, and then use the sum to products formula again. We get the final result. Okay, so it's not too bad for a warm-up. Problem 9b. Take the same sum, but continue it on to an nth term. So we stopped ours off at cosine 7a, but what happens if you continued through till the nth term? Well, apparently, the closed formula for it is just sine 2na over 2 sine a. Alrighty. Solution for this, or maybe just have a watch. So we can apply this formula just to show it works for our warm-up question. We've got 4 terms there, so apparently if we sub in n equals 4, this formula is true. If we cross-multiply that to take the 2 sine a up the top and then distribute the 8 that you'll get into 3 lots of 2, you can repeatedly use a double angle formula, which is similar to another question I've shown you over the last few days. And if you do that, you'll end up with sine 8a. The first term becomes, the term in red there becomes sine 2a, then it goes with the next term to make sine 4a, and then the next term to make sine 8a. Alrighty, for the proof though, when we have a finite number of terms up to the nth term, first of all, this isn't obvious to do. I've seen this before, probably stage 3 university actually. Let's consider a sequence of complex numbers. So where the complex numbers are cis A, cis 3a, and so on. Now, by the way that complex numbers multiply when they're in polar form, so for those of you who have seen complex numbers, you'll know this. When we times complex numbers in polar form, we add the arguments. So cis A times cis 2a is equal to cis 3a. So the sequence that I've created is a geometric sequence, and it's a finite geometric series that we're trying to find. The first term is cis A, and the ratio, each term has been multiplied by cis 2a. So we need to add up a finite geometric series, and the formula for it is that. Now, you can get that off Wikipedia. This might help for one of your assignment questions, but the general proof of it's pretty straightforward. You take your sequence, be careful of what you determine as n equals, the first term's n equals 1, but a lot of people will say it's 0. That means we actually only go up to r to the n minus 1. I spent 20 minutes trying to find a mistake in my working in the last half hour, and it was because I'd gone up to n. But we're actually only timesing by the ratio n minus 1 times. Times that whole series by r, and then subtract one from the other and divide, and we get our formula. Alrighty. In the infinite case, if you have an infinite geometric series, provided that the absolute value of r is less than 1, then it converges to that, because this r to the n term will go to 0 if r is less than 1. Alrighty, so we apply the formula. We can use de Moivre's theorem, which is if you power a complex number by n, or just think cis 2a times cis 2a times cis 2a, you add up all the arguments, 2a plus 2a plus 2a, n times is 2na. Expand those, and again we're multiplying complex numbers together, so we add the arguments there. And then lastly, the cis a is just shorthand notation for cosine a plus I sine a, so you can expand or write those in long format, which is going to help us. Okay, now we times by the conjugate top and bottom, conjugate of the denominator top and bottom. We actually only want the real part of this because we started with this complex number series. Alrighty, before I got rudely interrupted by the 5 minute cutoff, which isn't the first time that's happened, but I can't be bothered re-recording the rest of that to chop it down. We take this expression that we've got for the sum and we multiply by the conjugate of the denominator, top and bottom. What I was saying is that we actually only want the real part of this expression because we're trying to prove that cosine A plus cosine 3A, etc., which is all the real bits of the series that we're considering. So when we expand, actually only expand the stuff that we need, which is a real part times a real part, and then the imaginary part times the imaginary part, which, because I squared is -1, that will give us a real one. And we do need to consider the denominator as well. So the real part of S, that's a notation, RE of S, is equal to this series, which we're trying to prove, equals to something. Okay, so we take the real part of the left part of the numerator, multiply by the real part of the right part of the numerator, and likewise the imaginary times the imaginary with that minus. Be careful, I squared is -1. The denominator, because we're timesing the denominator on the left by its conjugate on the right, the real parts, all we're left with is real parts, and the imaginary bits cancel. So we end up with that. You can see straight away that we're going to get a cosine squared plus sine squared term, which will go to 1. Alrighty. Using, and the reason I've color-coded, using the sum to product formulas like we did in the warm-up question, we're getting minus NAs appearing inside the sine bits. We're going to get rid of those because sine's an odd function. We're going to take the negative out to the front. But hopefully you can follow through all of those things. 1 minus cosine 2a, I've just used the double angle formula there with a slight rearrangement to make it into 2 sine squared a. Okay, so we were there. Then, like I said, we use the fact that sine's an odd function to get rid of the minus inside the NA bits. I think that's all I've done in that step. Yep. I've also, you also see that there's a common factor top and bottom of sine squared, well, sine squared a on the left one, but on the right part is only a sine a. And we also know that we want our denominator of the thing we're trying to prove, the right-hand side, to be 2 sine a. So let's start by, hey, we're on the right track. So I've just cancelled some common factors. Okay, and then we have a common factor of 2 sine NA from both the numerator terms. So I factor that out. And then this is the, it wasn't so obvious, but when we've got a sine plus a cosine, and they're the same angles, it's actually the right-hand side of the compound angle formula for cosine. So it's actually cosine of n plus 1a minus a, which becomes cosine of NA. Okay, so there's a little bit of simplifying in that. But and then we've got the double angle formula in the numerator, sine 2NA over 2 sine A, and oh my goodness, 3 exclamation marks because it was so good to get through that. Hopefully you enjoyed that. If you'd like to do part of this yourself, then you could prove this result. It comes from the imaginary part of that sequence, but maybe start from scratch and see how far you can go on your own, because there was heaps of complex number stuff in there, and there was also the geometric series. So hope everyone's well out there, and yeah, good luck with that. Catch you tomorrow.